Hey everyone, welcome back for more AP Statistics. Today we're going to continue our look at the chi-square distribution with another reason that you can use the chi-square distribution, or maybe we should say it's another use for the chi-square distribution. So let's take a look. It's probably better just kind of looked at rather than just talked about. So here we go, more chi-square distribution talk. So, is the distribution between gummy bear color the same for Haribo gummy bears and Meyer gummy bears? Now I have to explain that Meyer is a kind of a grocery store brand. Here in Southern California, we probably would equate that with the Kroger brand. So it's kind of a, an off brand, not the name brand that Haribo is. So for a Haribo gummy bear versus the store brand gummy bears. Naturally, if we were in class, I would give you guys gummy bears, some of each, and you would do some counting for me. We'd collect that data as a class and determine if we have convincing evidence. So what we did is, as a small class, we counted the gummy bears, and we got that Haribo had 8 red gummy bears, 14 green, 15 yellow, 12 orange, and 6 white, for a total of 55 gummy bears. Whereas the Meyer brand, or Kroger brand really, had 10, 12, 17, 18, and 10, for a total of 67 gummy bears. So make sure you got that in your head. We've got one brand, Haribo, and another brand is Meyer. They came in different packages. So when we get to question 2, when it asks how many samples do we have, we actually have 2 samples. One sample that came from Haribo and another sample that came from Meyer. Question 3, how many variables are we examining? And think carefully about this one, because the temptation is to say red is a variable, green is a variable, etc., etc. So there are 5 variables here. But in reality, we actually only have one variable, and that one variable comes with 5 categories, the color categories. Now, like every other hypothesis test that we're going to be doing, we're going to need to write down some hypotheses for this significance test. So let's start with a null hypothesis. Somewhat different than our mean and proportion hypotheses. Our null hypothesis here is going to be the distribution of colors is the same for Haribo and Meyer. Now remember, colors was the name of the variable. Haribo and Meyer were the 2 populations. Alternatively, the distribution of colors is not the same for Haribo and Meyer. So this feels a little bit like our goodness of fit test that we just did in section 11.1, but now we're kind of comparing a distribution among 2 different variables. Now, before we had to write down our expected values, and we're going to have to do the same thing here, but for our expected values, it's kind of different, kind of weird, because we have 2 different variables. So let's just try to figure out how many red Haribo should we expect. Now, if the gummy bears come and they have the same proportion between Meyer and Haribo, then when we combine those 2 brands together, we should get something that's closer to the actual proportion of red gummy bears. Remember, we're going to assume in our null hypothesis that Haribo and Meyer both have the same probability, or have the same proportion of red gummy bears. So that proportion would be estimated as 18 out of 122. This is kind of like the PC that we did in our hypothesis test for proportions. Now we have 55 total Haribo gummy bears, and 18 of 122 of them should be red. So 18 out of 122 multiplied by 55 should give us the number of red gummy bears we would expect from Haribo. So we would expect about 8.1 gummy bears that are red from Haribo. We can do something similar for the Meyer brand, so we have 18 out of 122. That's the proportion we would expect to be red, multiplied by the total number of Meyer gummy bears, 67. And we get about 9.9 red Meyer gummy bears. That's what we would expect. Now let's move things.
To shop for 9.9.
Now let's take a look at the green gummy bears. The green gummy bears, we have a combined proportion of 26 out of 122 for green gummy bears. If we multiply that by 55, that's going to tell us about how many green Haribo to expect. So we would expect about 11.7 green Haribo gummy bears. Let's do that same calculation for Meyer. And we should expect 14.3 Meyer green gummy bears. Now, I probably don't need to point this out to you, but I will anyways. Notice that 11.7 plus 14.3, that does add up to 26. So the row total still adds up. Let's continue and find all of the rest of the expected values. Now we should probably think about a formula here that's going to work. So let's start backwards. That green cell would be the expected count. Great. The next thing we see are the blue and yellow. Most of the time we organize it so the 16 and the 67 are both on the numerator. Mathematically, that's the same thing. 16 is the row total. 67 is the column total. And 122 is the table total. Altogether, we have our formula for the expected count for any population and category. It's the row total multiplied by the column total divided by the table total. And now we're ready to go to our 4 steps. So here's our 4-step plan here. First thing we're going to do is we're going to state our hypotheses. So the null hypothesis, the distribution of colors is the same for Haribo and Meyer. And alternatively, the distribution of colors is not the same for Haribo and Meyer. No significance level was provided for us, so we're going to just test this at the 5% significance level. Alpha equals 0.5. Our 2 conditions, they are random samples and large counts. We say that both Haribo and Meyer came from random samples. Notice that both populations have to be from random samples. And for large counts, all of our expected counts are greater than 5. You would point to a table of expected values somewhere in your work. Let's talk about the specific formula now because we're finished with the plan part. The specific formula is actually the same. Chi-square is equal to a sum of all the observed minus expected squares over the expected. Now for the work, since we actually have quite a few different categories, we have 5 for Haribo and we have 5 for Meyer, we're just going to do a few of them. So let's see. There's the red gummy bear from Meyer. Here's the red gummy bear for, no, the first one was the red gummy bear from Haribo. The second one is the red gummy bear from Meyer. Here's green Haribo. And then from here, since we've already done 3, obviously we have a lot more to go. We would just put the very last one in there. So the very last category, that is white Meyer gummy bears. And there were 10 counted. 10 observed, 8.8 expected. And then we would add all of those together. Naturally, you have much more than what you've written down here, but if you do them all and add them all together, well, we would get 15.36. Sorry, 1.536. Next, degree of freedom. Now this is a new formula. This formula for degree of freedom is row total, number of rows minus 1, multiplied by number of columns minus 1. So for us, this would mean that our degree of freedom would be 5 rows minus 1 multiplied by 2 columns minus 1, or just 4. Next, the picture. We would put a blank chi-square curve, and we'll really do the rest of this later. Next is the test statistic. Our chi-square test statistic is 1.536. We figured that out earlier in our work. And lastly, our p-value. This is going to be the proportion on the chi-square curve that's greater than 1.536. And that's going to be 0.8203. Now that you have your p-value, it's probably a good time for you to fill in the rest of your chi-square chart. So we're looking for a place that has 82% of the area to the right, and probably about 20% of the area to the left. And I would probably estimate that right about here. We would call this chi-square equals 1.536. We would call this the chi-square curve with 4 degrees of freedom, and we would shade over here on the right side. So this is the kind of curve that you would expect for this kind of test. Now, conclusion, that's a pretty big p-value. It's definitely greater than 5%. Since the p-value is greater than alpha, 82% is greater than 5%, the data does not support that the distribution of colors is not the same for Haribo and Meyer. And the last deep thinking question here is, explain how this test is different than a chi-square test for goodness of fit. And so the thought here is that the chi-square goodness of fit test only has one population and one variable. But for this test, we have one variable, but it's spread out among 2 different populations. Remember, we had the variable that we were examining was gummy bear color, and the 2 populations which we were testing, whether or not they were the same, we were testing the Haribo population and we were testing the Meyer population. So this test that we just did, it's kind of like a double goodness of fit test, really. So hypotheses. This was called the chi-square test for homogeneity. Okay. And again, this is like doing multiple chi-square goodness of fit tests. So for the null hypothesis, I'm sure you can read, this says that there is no difference in the categorical variable distribution for population 1 and population 2. And alternatively, there is a difference in category distribution for population 1 and population 2. We talked at great length about the expected counts. That's just the row total multiplied by the column total divided by the table total. The degree of freedom, number of rows minus 1 multiplied by the number of columns minus 1. And the p-value is computed exactly the same way. And the chi-square test statistic is computed in the exact same way. Which makes us wonder which test is which. Well, when you have one sample and one variable, that's the chi-square goodness of fit. When you have 2 samples and 1 variable, that's the chi-square homogeneity. And actually, we could even extend this to 3 samples and 1 variable. So as long as there's only 1 variable, it's a chi-square test for homogeneity. Now, we're going to go ahead and take care of this really quickly. For a class project, Abby and Mia wants to know if gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half the males were randomly asked, what would you vote for a female president by a female interviewer? And the other half of the males were asked the same question by a male interviewer. The table shows the results. State the appropriate alternative and null hypotheses. Well, what are the 2 populations? Is the population the yeses and the nos? Or is the population the males and the females? And I think you should know that the population are the males and the females. So our null hypothesis needs to be the distribution of responses is the same for the male interviewer and the female interviewer, which means the alternative hypothesis would be the distribution of responses is not the same for male and female interviewers. Show the calculation for the expected count for the male yes cell. This is a very common question. No one wants to, really look at all of your calculations, but they certainly can ask you for just one calculation. So what is the male yes cell calculation? Well, it's going to be 50 times 69 divided by 100, which equals 34.5. Now we just have to do the same thing for the entire table. Our expected counts should be 34.5 and 34.5, 5.5 and 5.5, and 10 and 10. Next, calculate the value of the chi-square test statistic. So this is going to be a pretty long string. We're going to put the entire thing down here for you. So we get a chi-square test statistic of 4.246. So this is the end of our Stats Medic today for 11.1. Just the nuts and bolts, the basics for us doing our chi-square test for homogeneity. Hopefully you're finding it easy, and I will see you next time when we hit the last section here on chi-square distributions. Have a good one.